So we have many different ways of solving the same problem. And obviously some of them are correct, some of them are not. But even among the ones that are correct, there are some that are faster. And we want to know why. And some of them are conceptually easier to write. And sometimes an easier solution may be better because you can write it quickly, you can check it, and you can use the output to test for a more complicated solution. So because of that, we would like to generally think about how to solve something. And so basically, we are going to first start by writing a simple piece of code, and then writing in various ways. And then we are going to look at how long we think it's going to take. We're going to talk about complexity yet again. And you cannot get away from complexity if you're a computer scientist. If you're writing programs, you have to worry about how fast it's going to run. So generally speaking, whenever you are executing a program, you care about how many operations you are going to do. Okay? Generally, we don't know how many operations, but we can look at, given a list, let's say, how many times over that list you are going to go over. If there are n items in the list, how many times over the list you're going to go, and whether we can find out how to really understand this order of notation, order of n log n, order of n squared. So we are going to basically look at a very simple problem, and then we are going to do testing, analysis, and in fact timing. So 3 different ways of looking at the same problem. Okay, so we are going to start very simple. We are going to first write a few functions to find the index of the 2 smallest values in a list. Okay. So there are many different ways you can solve this. I want to hear at least 1 or 2 from you. So you are given a list. It has numbers. You don't know in which order. Okay, we will change that later. And then you want to find the index of the 2 smallest values. So, shout out algorithms to me. Yes. Can I sort it? But if I sort it, I will lose where they are. But what can I do with a sorting? With sorting? You can sort it. Then. Okay, so that's good. So we are basically starting with what we call an algorithm, right? So let's try to write down these algorithms. Okay, so we can figure out what we want to do. So generally, your solutions start with an algorithm. You don't even have to write the whole code, especially if that code is complex. But you can at least, write down what you're going to do. Eventually, when you become good programmers, writing an algorithm will be just implementing it in Python before you implement it in C. But for now, we will start with even writing before we write it in Python. So we said, make a copy of, so idea 1. Make a copy of list. Sort the copy. Okay, what's the next step? Okay, I'm going okay so far. What's the next step? So I can find the 2 smallest values, right? Then what do I do next? Okay, so the problem is find the index of the 2 smallest values. Okay. So once I find the smallest values, what do I do? Yes. You iterate through the list. There is a list.find value because it's Python. Okay. Find the value. Find the index of these values. Okay, and we have to see if that is easy to do or not. We will think about that. Okay, so this is idea 1. And there is a find value. Let's see. Is there a find value? 1, 2, 3. Is there a find one? There is no find. What is the function that has this? There is an index. That's right. And index will return error if it is not there, but it will find you the index. Ultimately, you will learn that these are actually all implemented functions that you can write easily, but that's okay. All right, so this is algorithm 1. Give me one more algorithm at least. Okay, so this is one way you can do this. Yes? Can I just remember the last two indices that I have the smallest possible value so far? So like I do what you're saying, but instead of putting them in another list, I just basically keep two variables. Yeah. Okay. I'm happy with that. So this is idea 2. Initialize two smallest values to 0, 1. Then iterate through list, and remember the smallest two values and their index. All right, do you have any more ideas? That was not one of the ones I came up with. I like that too. Of course, this is what I've been telling everyone to do, right? Okay, I like that one. So make a list of value index, sort the list, return the index for the first two. I like that. That's actually very simple. Anything else? Any more ideas? I will definitely implement the first 3. There was a fourth that I wrote, which was actually much more complicated than this one. I like this one better. So what I can do is I can find the minimum value. I can find its index, right? You know how to do that. So you know there's a min function, there's an index function. Then I remove the minimum from a copy. Then I find the next minimum and then find its index, something like that. Okay, so make a copy of list, find min, find index of min, remove min from list, copy, find next min, in copy, and find index of min in the next copy. Okay. So anytime you're implementing these complex algorithms, you also have to test them thoroughly. So this is where the nose module comes in. So generally, you can write test modules one by one, but you can also write the list of things that you want to try before you start. Yes? It may change. In fact, all of these algorithms have places where they may fail. Okay? So this is the interesting next case, right? All of these are basic ideas, but you have to refine them as you implement them. And there are many ways that the other algorithms may have problems. Okay? Like find the index of these values. There may be an issue with that one too. So what we are going to do is we are going to think about what are the types of things we want to test this on. So what are the ways that input can be challenging so that we can write test cases for them. So you can write your test cases by basically writing inside if name.main. This is generally where you can write test cases. Or you can actually write a test unit test module. So this is where nose comes in. So you can actually decide what are the types of things you want to test this on, and you can write a test module. So we are going to use nose for this. So what are the types of lists that I should use to test this on? Give me examples of lists that will be challenging. So generally speaking, when you are testing cases, you have normal test cases, and you have edge cases, meaning that unusual cases. Okay? And unusual cases are generally much more important than the usual cases. So here I have this one for you that you may like. QA engineer is basically a quality assurance engineer. This is the person who tests your programs. You will come to hate them. So you have to find test cases that are completely weird, and you must not assume that these test cases will never occur. Okay? So you may assume that some may never occur, but if you're really testing something in the real life that's going to be used by customers, you cannot assume too much. So even in the case of just a list of integers, what are the kinds of things I must test? So the usual cases would be that I have a list of values, and the values may or may not be ordered. And I will put the smallest values in different places. Okay. So one of the things that I can test is, for example, the two smallest values can be at the two extremes on one side. So like 1, 2, 3, 4 is on this side. I can also look at the reverse. Or I can look at something like 2, 1, 3. So 1 and 2 are on both ends or the other ends. So generally, if you are iterating over a list, you want to make sure that you actually are hitting every single value. So you can have, for example, something like this. So, I have it at the one end or on the other end, on two ends, things like this. What are things that I can test? Give me some other ideas. Yeah, the words you can test, but I'm not going to because that will take me too long. But yes, what if it doesn't have numbers, right? But sometimes you have to make some assumptions, right? But hopefully above this point in your program, you will test that's not true. But yes. Repeated values, right? That's an important one. What happens if you have 2 zeros or 2 ones? So what about you have, this is where it's going to go into interesting issues. So let's say you have 2 ones, right? Anything else? What are some weird cases? Negative numbers. Well, negative numbers still can be ordered. So I am not so worried about them. But how about how many values are in a list? What happens when you have a list of 1 value or 2 values, right? Does it work? So I would test for smaller cases as well as big cases and hope that it works. But this also gives you some idea of how you're going to implement this. So for example, what should you return if it is empty list? Okay, so you have to decide what this is. So let's say I'm going to return none in these cases. Or that since I'm going to return 2 values, I'm going to return none and none. That there are no 2 smallest values. So you have to decide what they are before you start. Okay? So, so we are at least going to do some of these so you can see how nose runs. Okay? So the nose test cases I'm going to write in a separate file. That file is generally named test underscore something, filename.py. Whereas my regular file is called search.py. So test search.py knows that it has to test search.py. Okay, so let's write the first algorithm. Make a copy of left. So I'm going to call the search smallest to 1. We'll take a list. I will make a copy of L, and then I'm going to sort L, and I'm going to call min1 and min2. They are going to be L1 of 0, L1 of 1. Okay. So now I'm going to find the index of these. So I'm going to find, how am I going to find the index? So I can find the index of L1. So I can say I1 is L1 dot index of min1, and I2 is L1 dot index min2. Return I1 and I2. Okay? Yes? Oh, sorry. Yes. It should be the index in L. Thank you. Okay? And now I'm going to write my test cases in the other one, just so that we can see if this works or not. So now my function is called st1, right? So what I'm going to do here is I'm going to import nose, which is the test module. I'm going to import all the functions from search. And now I'm going to write functions. Every function that I write should be named test something. So I'm going to call it test st1. And then I'm going to have multiple of these, so I'm going to write them like this. Okay? So whenever you run nose, it's going to run every function that has a test on the top. So basically the idea is that if I run st1 on 4, 1, 2, 3, what should it return? What is the index of the two smallest values? It is 0 and 1, right? This is what I expect. So I'm going to assert that when you run st1, the output should be equal to this. So assert means that if this is true, then this function will succeed. Otherwise, this function will fail. And I'm going to run one more here. So I'm going to write 1, 2, 3, 4. In this case, this is not correct. This should be actually 1, 2, right? Because this is index 0, index 1, index 2. This is 0, 1. Okay, let's write one more. And in this case, I am going to have another 1 here. And if I have 1, 2, 3, 1, the smallest value is 1, and the next smallest value is 0, 1. No, it's at 0. The index is 0, 0, 1, 2, 3. Okay? Are you okay with me so far? We agree? Okay. So now I have to tell the nose module to run. Okay. Now, normally when you advance in programming, you are not going to run nose from command module. You are actually going to run it on command line. Okay. So you're going to basically do something like nose tests test search.py. Okay. So this is the normal way you would run it, but unfortunately we have not taught you how to use command line, so we are going to show how you do it. Okay. And it will tell me that it ran three tests, but one of them has failed. And the one that failed was this assertion, right? So this test case was wrong, which is actually this one. Okay? Now, if you want to run the same thing, have the same effect in nose, what you would do is, okay, let's see. You would do this, which is not actually the standard way of doing it. Because of that, it's going to lead to some weird error. Okay? So this basically just does the same thing. It has the same effect. But after it finishes, it will give you some random error, which we will disregard. Okay? So it basically did the same, right? It told you that in line 29, there is an assertion error, which is this one, okay? But then it gave you all of this failure that we can just disregard. Because of the way we are running it, it just does this. This is the only way we figured out how to do it, okay? Well, all I care is that this one has failed, okay? So from this point on, I'm going to not use this, but I'm going to basically use the command line version. So why is this failing? Okay, let's go back to this one. So why is this one failing? This is the case where you have a duplicate value. Okay. If you want to see what happens, we can actually try the same thing here, right? So SD1 of 1, 2, 3, 1. In fact, it returns you 0, 0, because it will always return you the index of the first value, right? So you can solve this in one of different ways. So I don't know if you can actually, in index, okay, you can actually give a starting point, meaning that start from this value and find the next. So for this to work correctly, you actually have to tell that start in I1 plus 1 and then find the next. Okay, so now it is correct. And now you can see, hey, that should be correct. What did I do wrong? I can see it's returning 0 and 3. It's not saved. Okay, yes, I'm stupid. Okay. So now all the 3 tests are correct. Okay? This is what I expect all of you to do for all of your functions that you write, but I'm going to now go a little faster because I don't have time to write all of these. But this is kind of the basic idea, and I will post more test cases online after I'm done. Okay? But you see that this allowed me to quickly find a problem. There are other test cases that I wrote that I know for sure that this is not going to work for. For example, I know that it is not going to work for this one. It is not going to work for this one. It will hopefully work for this one. There's no reason why it shouldn't. Okay? So let's think about what is the complexity of this solution very quickly. Okay? So whenever we think about complexity, we always look at the number of items in the list. Okay? So let's analyze this. So assume n items in list L. Okay? So if there are n items, I want to figure out as a function of n how many different operations I do. Okay? Every time I read a value, I check a value, it is a function. Right? So it is something that costs time. So for example, if I do this, what is the complexity of this? So I have to read every value in the first list, make a copy in the other list. So take one value, read it, and then append it to the end of the second list. So this function, since it reads and appends, for each item you have a cost, right? So this has some sort of, a cost that is order of n, meaning that you do something for each value in the list. The second thing that you do is, for every value, you're going to take this list and you're going to sort. It turns out that sorting is more expensive than order of n. For now, you don't know why, but accept that it is going to be called order of n log n. And we are going to do that this Thursday to see why it's at order of n log n. So order of n log n means that it is more expensive than order of n, but it is cheaper than order of n squared, which is double loop. Okay? So then I get the first 2 items. That's a cheap operation. You just read 2 values by accessing it by index. So this does not really cause any kind of problem for me. Okay. Then you need to find the index of the smallest value. What happens if the smallest value is at the end of the list? So I have to read still every single value to check if it is equal to that value, right? Yeah? Okay. So in fact, this is likely order of n. Now, if you are very lucky, sometimes you will be very lucky and it will be the first item. Sometimes you are very unlucky, it will be the last item. And if you do this enough times, you will generally find it somewhere in the middle, right? If all the locations are equally likely. This is why we make our students take probability, okay? So generally speaking, even if it's halfway, it is still a function of n, so it's generally considered a linear operation. And then the same thing is true for the next smallest item. That can also be almost at the very end. So that is also order of n. And so this is cheap. So if you look at this, so the way that you read complexity is, you have 1, 2, 3 order of n steps, so 3 times order of n, plus order of n log n, okay? Since order of n log n is generally so much more expensive, it's generally like order of n log n plus some expensive stuff, right? So, you know, you can say this is order of n log n plus 3 times n, but generally the 3 times n is not, you know, which is almost the same as order of n log n. Okay. Any questions so far? So basically, if you have order of n log n plus a few order of n things are so cheap that they don't count when you have the order of n log n. If I had an order of n squared, order of n log n will not count.
I have a question. It doesn't pertain to the order, though. It pertains to the load testing. So if you have a list that's such that you're doing the distance tests, the minimum distances, and it returns more than just 2 points. So for instance, 0 and 1 and 1 and 2, both have a distance of 1. How does the nose test those things?
So you have to write an assertion of exactly what it will return. Okay, so you have to assert that exactly for this list, this is what I expect.
So would you? Okay.
So you have to know what it is, exactly. And it's kind of a, you know, knowing where you are. But, you know, unit testing is actually difficult. Sometimes you're writing unit testing, you actually are first debugging your unit tests. But once you set your unit tests, then as you change your program, you don't have to really think about what you need to test one by one. But it is tricky, right? You have to think exactly what it should return. And you have to set that up. So it is kind of a, you know, at first it's a little confusing and, you know, it's not maybe worth in the long term for such simple functions. But for complex software, it's very important. So, all right, so let's do idea 2. So I am going to do the second idea. Okay. So I'm going to have to set min 1 and min 2, right? So I'm going to set them to be the first 2 values. But I have to figure out which one is smaller. So if L0 is less than L1, min 1, min 2, I'm not going to even keep track of I1 and I2. I'm just going to the values. I'm going to keep track of the minimum values. Okay. So for the first 2 values, if the first value is smaller, then the minimum value is at 0th index, the second value is at the first index. So now, I'm going to go through the remaining values, starting at 0. And now I'm going to basically ask, if L of I is less than L of I1, if the first value is even smaller than my smallest value, so then I'm going to shift the values. I2 is no longer the second minimum, I1 is the second minimum, and this value is the first minimum. So I1 and I2 is going to be I and I1. Right? I2 is shifted out. If this is not the case, the other thing that I care is if L of I is less than L of I2. In that case, it's not smaller than the smallest value, but it's smaller than the second smallest value. In that case, all I care is that I2 should be I. And then I am going to return I1 and I2. If you want to actually test, you can just change these to 2 and do the same, and they still seem to work, so I don't need to do more testing. So this is fine. Say it again? Because I already have checked 0 and 1. Right? So when I'm iterating through the list, I don't need to look at the first and the second value, but the third value in the list. Right? I'm not being extremely conscious of complexity. Right? Anything else? Okay. Let's think about the complexity of this one. Okay. Can you tell me what's the complexity here? Okay. Do we agree it's order of n? Each item I go through with only one time, right? Every item I go through, I do 1 or 2 if statements, right? It will matter how many if statements in the long term, but for now, it is just order of n, and only once, right? The other one, I had order of n at least 3 times, but here it's only once. So basically, this whole part here is order of n for the whole loop, and that's it, right? So this is actually, should be cheaper, but we will see if that is true. Okay, and then let's write the third one, and I will leave you to write the fourth one. The fourth one is tricky because of what, where is you? But you pointed out. Trying to figure out where you are. The one with the, no, he's over there, but he's buried in his code. Okay. All right, so now let's do the last one. So I am going to do this very nice algorithm. So in fact, I'm going to do this in even a slightly different way that you may not have seen, but it's actually super useful. Maybe by now you should learn it. So I want to iterate through indices and values in a list, and then put them in a list. So what you can do is you can actually do that by this function called enumerate. The enumerate will actually return you index and value pairs. Once you get used to it, this is actually much easier to write than for I in range of L, use the value. So this does the same thing. Okay, so I am going to append into I value in I, because I want to sort by the value first. Then I'm going to sort L1 of val, and then I'm going to return L1 of 0 of 1 and L1 of 1 of 1, right? Because the first zeroth value is the value, the I is the index. Okay? So here it is. If you want to see in action, here I'll show you. For I val in enumerate dog, cat, and pig. So this is how enumerate works. Okay, it enumerates indices and values together, which is very, very easy to do. It turned out that ST3 was actually exactly 5 lines. Okay, if you want, I can test that one too. Of course, you should really write different test cases for each, but I can test this because it's easy to do. Okay, those are also correct, so I don't need to do more testing. Okay, any questions so far? What's the complexity of this one? So what is the complexity of these 2 steps? Bless you. So these 2 steps are similar to this, right? the same kind of deal. You go through one, copy it into another one. Append is generally very cheap, order of 1. So this is actually an order of n step. Okay, and the sort is always order of n log n. Well, what you're sorting is actually twice as long. It's comparing two things, but twice as long is probably not that important. But this is slightly more expensive because you're actually sorting a list with more stuff in it, so there's more if statements, more comparisons. But overall, ST3 looks very similar to ST1, except that ST1 maybe had a few extra steps here and here and here, whereas this one has sort over a more complex list. So they are going to be very similar. Okay? Now, this is kind of what we do with complexity analysis, right? So you try to look at how many times something happens. If I were to have a double loop, for some number of n, let's say 100, okay? This is what you need to do for your lab. If you actually had a program like this, now this program is a little different because the J loop you are executing how many times? N times, right? And then that loop itself you are executing how many times? N times. So you are executing a total of n squared times, right? Double loop is n squared. All right. So what we are going to do is we are going to actually write code to test. So we are going to run these algorithms to see how long they take. Okay? So to be able to do that, I am going to first create a list. It's up to you if you want to have duplicates or not, but I'm going to create a list that doesn't have duplicates. Let's say 1,000 values. But then I'm going to take those values and I'm going to shuffle them so that they are not necessarily in the same place, the two smallest values. So if you want to shuffle, you need to have the random module and then use random.shuffle, which will take the list and randomly shuffle the values in it. If you want to see how that works, here I'll show you with a smaller value. Okay. Every time you run, it shuffles. It's a slightly different random order, right? So we can do slightly bigger cases. So what I'm going to do is, once the list L is fixed, I am going to look at the time, the clock time of my computer. Then I'm going to run one of the algorithms on this list. Then I'm also going to look at the time after the algorithm ends. Then I'm going to print how long this took. Let's see. So the time module does many, many things. It basically uses your computer's time, the clock, and it will take the time. In one of the functions that I gave you, in one of the programs, there was also this thing called time sleep. Did you see that one? The one that basically had these different problems. So let's see. So if you were to so this was the function that this was one of the eggs that you would have found if you had done this. Okay, I don't know. Have you done this? So the reason why this is coming in these short steps is that the program is actually stopping at different times. That is also the time module. So if you wanted to see, this is what causes that. I'm telling the program every now and then to sleep for 1 second, right? So a lot of things that have to do with time is implemented in this module. So for this one, what I'm doing is I'm basically looking at the time before and after I run and then print out how many there is. And I'm going to do the same thing for all the remaining functions. So I'm going to run st2 and st3, and I'm going to look at how long they took. So our expectation is which one is the fastest? 2 is the fastest, right? All right, so let's try this. Okay, what we did not do is all right. Well, I seem to have a bug in this one, right? This is line 48. I'm going to say that they were next to each other, so I should have started from I1 further. All right, there we go. Okay. So, ST2 didn't take too long. ST3 took a long time. Okay. Well, there's something wrong with this. So I was very excited that this was actually correct, but I keep getting an error in this one. Oh, yes, yes, thank you. Ah, that's awesome. All right, so what we need to do is, you're right. So we are going to first look for the value, and if I2 is equal to I1, right, then I'm actually going to look for I2. Okay, I was going too far with this one. All right, like this, right? So I should not assume that min 1 and min 2 are the same. That was stupid of me. Thank you. All right. Would have taken me a while to look at that. All right, now it looks better. Okay. So one of the things that you see is that there is differences, but I am not sure if I'm seeing the differences well enough. So one of the things that I'm going to do is I'm going to actually increase the size here by adding some zeros. So because I'm searching for one thing, it may not be sufficient to see this with a small enough data set, so I'm going to run some bigger data. Okay? And if you make this bigger and bigger, eventually it will be very, very slow, but I'm going to do one more order of magnitude. You can see the differences really grow. Some are much, much faster than the others, and some are a lot worse. I thought the ST3 was going to be a great one, but it is pretty slow. Okay? Why is ST3 so slow? Because this sort algorithm is likely very expensive. Okay? Because now it's checking for two things, right? It's checking for the smallest value and then the second. So it has a complex comparison for every single element. Even though it's n, there is a constant element that's very, very high. So as a result, this one actually is taking a long time. It's taking 3 times longer than this one, which looked similar, but it's different. And in fact, it is my fault that I keep telling you to do everything like this, since like homework 3 or homework 4. But in reality, this is not actually a cheap way to do things because of how Python implemented pairs of sort. Whereas the first one, it's a little better because you're sorting a single value, right? You're sorting a list of single values. That's a different implementation. Well, what we do know is that this is much, much faster, right? There is no comparison because it's order of n, and it grows linearly. So what that means is, if you want me to show you, okay, I'm going to just run this one time, okay? So let's run this for 100,000 elements. Okay, it takes about 0.08. Now I'm going to add 10 times. I'm going to increase it by one scale. Okay, and it's now 10 times slower, right? So it was 0.08, now it's 0.7. So if the input is 10 times larger, it's 10 times slower. It's taking 10 times more work, right? If I scaled it 2 times by 100, it should be 100 times slower, 100 times faster, right? This is what it means linear, because I can expect how much it is. If something is n squared, so if I increase it by 10 times, it's going to be 100 times slower, right? So that's why we want algorithms to be as much as possible, as fast as possible. Okay? So please do take the effort to do the IDF4 and then make sure it runs. But now I'm going to write a different algorithm, which is going to be kind of interesting because every single time I write this algorithm first time, I write it wrong. So
I ran the 3 test cases for about 10 million elements, and yeah, ST1 actually came in slightly slower than ST3.
I do not know why. So this is an interesting question. There are many things that could be true. Okay, it could be that this implementation may have slightly different version than yours. So their implementation of sort can be different. So your Python version and my Python version can be a little different. The problem with doing complexity with Python is the following, that a lot of these algorithms are implemented in C and then compiled into Python. So there are some hidden reasons why that is the case, and it's not always so easy to explain. When you take data structures, that's much easier to see. Okay? With Python, there are some issues. Sometimes you may see different ones. So my guess is the difference is the implementation, but you and I may not have the same version of Python. Okay? But you have to be very careful when you do these things that there is a little bit of hidden stuff under the hood in Python that makes life a little more complex. And we will talk more about that when we do sorting. So when I do sorting, there was this one thing that I discovered last year. It took me forever to figure out why one algorithm, seemingly faster, was actually slower. So I actually asked Professor Anna Milanova, whose research is this, and then she researched it, and then told me that there was this one method that I used was actually very slow. So there are all these like weird things that happen. So you have to accept certain level of uncertainty also. Okay, so now we are going to do one final thing, but this is going to take us a while, and I hope that I will not mess it up, but it is likely that I will mess it up, so then you will have the joy of seeing how to fix it when you mess it up. Okay, so now we are going to write a much simpler algorithm, which is given a value, I want to find the location of that value. Okay, so you basically say just return index, right? Okay, so what if I want to not just return you where the value is, but I also want to return you where the value would be if it was in the list. Okay, so where I would insert a value if the value was in the list, right? So let's say you have this list here. So if I ask you for, let's say, 11.9, 11.9, if it existed, would go between these two values. So I will need to return the index of this value, which is 0, 1, 2, and 3. Okay? So I'm going to write something slightly more complex. but I'm going to assume the values are sorted. So this is the important part. So let's write the simple algorithm first, and then we are going to go further. So find the index of value if value is in list, or if it is not, return the index. So input, all right, let's write this. Input is a sorted list and a value. Okay, so find the index of value if the value is in list, or if it's not, return the index of where value would be inserted to keep the list sorted. Okay. The problem with CS1 and Python is that it's very hard for me to come up with algorithms for which there is not a single line solution in Python. So we try very hard, but sometimes makes life more complex for us. So let's write this very simple. So I'm going to say search L and well. Okay. So for I and, well, we can do enumerate version. But don't panic. I know you're going to panic that this is now, you should learn this for the exam. I was just doing it so you see something different, but let's do it the other way. If you become an expert in Python, you actually use enumerators all the time. That's like Python's way of making life easy. But for what we do in CS1, we don't need it. Okay? So if L of I is greater than or equal to value, I'm going to return I. Right? So for every value, find the first value that is greater than the value that you're searching for and return it. Is it possible that I go through the whole list and never find a value that is greater than? Right? Because if I was searching for 20, there will not be a value greater than, right? So that means if I came to the end of the list, then that means I have not found anything. Then in that case, I should return what? Right? Is it length of value? No, it should be length of value, right? Because I would insert it after the last value, right? All right? Well, let's search. So if I was searching for, let's say, 1, it will return me 0 because I would insert it at 0. Okay. So if I was inserting it, I would insert it at 0. If I was searching 0, if I was searching 2, I would also insert it. It is also at 0. So whatever function I call this in, I have to check if the value that I'm searching for is there or not. And I think I should return length minus 1 here. So if I was searching 4, so if I was searching 3, I would insert it between 2 and 4, so I should return 1. If I was searching 4, that should also be 1. If I was searching 6, that should be 2 because I would insert it between 4 and 8. Okay. And what if I was searching for 10? Should I return, I would insert it here before this value? No, after this value, right? All right. Now I'm making decisions on the fly. But still, apparently, I am unable to write this function. All right. There we go. Okay. So what's the complexity of this search algorithm? What is the worst case? The worst case is you go through everything, which is order of n, right? In the best case, you go through nothing. Just look at the first element. In general, let's say you go through half, which is still n over 2, so this is order of n, right? So this is a linear algorithm, which we know is good, but asks for if there's a better solution, okay? So there is a better solution that doesn't require you look at everything, okay? This is where things get more interesting. So how could you not look at everything? Have you ever played the guessing game? Because you actually have iPhones, you don't have to play guessing game or other boring things like that. So you guess a number between 1 and 500, okay? Then I tell you 250, and you tell me if it is bigger or smaller than that, right? Do you know this?
Yes.
All right. I know it's lame because we didn't have iPhones and, Netflix. So then I say, okay, if it's between 250 and 500, next I'm going to look at the middle value between those two, and then you tell me if it's to the left or right, okay? So at every point when I'm looking at this, I am actually reducing the scope of how much of the list that I'm looking at. So this also is done very frequently when you are searching in a dictionary, which again, you never really touch in physical form anymore. But if you actually had a physical dictionary and you're looking for something, you generally guess where you have it. And then you basically go to the front or to the end, and you can keep searching to the different parts of the same thing to reduce it. Because the reason why you can do this, because it is sorted, right? So if you have a sorted list, and you have, let's say, 0, and this is the last element, n minus 1, and you're searching for some value, let's say 50, okay? You really don't have to look at the whole list one by one, because it is sorted, right? I do know that it is a sorted list. So what I'm going to do is, I'm going to find the middle value. And I'm going to check if the middle value is less than 50 or greater than 50. So if the value is greater than 50, then I know that the value 50, if it exists, must lie between these two values, right? So now I can actually change and search between 0 and the middle value. So that means if I started with the bounds, let's say low and high, between 0 and n minus 1. So at first I knew that the value was between 0 or n minus 1. Now I check the middle value. If I check the middle value and it is actually already greater than 50, then it has to be between 0 and mid value. Okay? In fact, it's probably to the left of the mid value, so mid value minus 1. So the next thing that I can do is I can check, for example, the middle value between these. Let's call this mid 2. And let's say this value is actually less than 50. So now I know it must be in between these two. So that means I need to now move the lowest value to M2 plus 2. Okay? So now it's between mid value minus 1. Okay? So the idea of the algorithm is that always look at the middle value and adjust the low and the high end, right? So you have the bounds, but at first you're looking at the whole list, but then now you're looking at this half, and you're looking at this half, you're looking at this half, and eventually you want to come to a point where they are both pointing to the same exact value, and such that either that value is the value you're looking for, or if it is not, then it would have been there. The value would have been there. So you don't actually have to look at every single one. Okay? So let's see this in action, and then we will write the algorithm. So let's say I have a list. Okay. Okay. And which value I'm looking for? Let's say 16. I'm searching for 16. So I'm going to have a low value and a high value. So the low value is pointing to this one first, 0. The high value is 0, 1. So you have 0, 1, 2, 3, 4, 5, 6. So the high value is 6. So the middle value is going to be half point between them. 0 plus 6 divided by 2 is 3. Okay? So middle value is 12. Okay? So is 12 greater than 16? No. So it should be to the right of 12, right? So what I'm going to do is I'm going to move low from here to here. High is still going to be here. So now low is going to be 3 or 4. I've already checked it's greater than 3, right? So I'm going to put it at 4. This is where things go badly. You will see in a second. So, and then 6. So I have 4 and 6. What is the middle value? 5. Okay, which is actually this. So now I'm going to check 4 and 6. Is it less than 5? 16 that I'm looking for is less than 5. So it should be to the... So I'm going to set high to 4, because it should be to the right, and set this one to 4, right? Is this correct so far? Because I already checked that it is less than this value. Okay. And now it is 4 and 4, so that is here. It either exists or it would have been inserted right after this point. Okay. Now the problem is that this algorithm hides a small complexity. Okay. But this is really what I would like to write. So I'm going to write this first, and then you will see that this will not work. I've done the bad version so many times that doesn't require a problem. So let's write this one. Okay. Now I'm going to write the binary search. I'm going to set the low value to be 0, high value to be length of L minus 1. So while low is not equal to high, so the idea is that I'm going to keep iterating until they point to the same exact thing. I'm going to find the mid value to be low plus high divided by 2. And then if L of mid value is less than value, so the middle value is already less than the value, so what do I do? So which one do I move? So middle value is already less than the value, so value is to the side, so I have to move to low, right? So move low to mid plus 1. Else, I'm going to move the high value, and I'm going to move the high value to middle, okay? Because I haven't checked for equality. I don't know if it is equal or not, okay? And then when I'm done, I'm going to return no. This algorithm is not guaranteed to end, okay? You can test it with a few values. What I recommend you do is, when you implement algorithms like this, print these values, and then actually read for input so it doesn't go on forever. Okay, and I'm going to do this. Okay, so 0, 2, and 1. That worked. Right, let's do this one. Did I write this correctly this time, just for the sake of it? Right. All right. It is so easy to write this buggy, but it's not buggy right now. It may still be buggy, but we will see. Okay. So we are going to test this the next time. But I want to do one final thing before I go. Okay. So this is one of the very basic algorithms that is kind of so simple, but it's also very tricky to write wrong. Okay. So don't move yet. I had to wait for the whole, the psychology class. Give me like 2 minutes. Okay. So let's look at complexity first, and then we will look at the problems later. So if I have n elements, do I look at all n elements? Because in the first thing I do is I look at the middle value, then I decide I'm not even going to look at half the list, right? Then I'm going to look at the remaining values. Of the remaining values, I still decide that I'm not going to look at half. And I keep dividing this by half until there's only one element left. So let's say you had 16 elements. So how many times can I divide that by 2? 16, 8, 4, 2, and 1, right? Because 16 is 2 to the 4, right? So that's the number of times I can divide the list. And when I come and I can't divide anymore, I return. So given n, I only look at which power of 2 the n is. Do we understand this? So instead of looking at n items, I actually look at log n items and log base 2 n items. So this, in fact, should be much, much faster than the other search. And if you don't believe me, run the test code and then look at how much faster this is. So the most important thing to remember is that this is order of log n. Much, much faster than the previous algorithm. Okay? So we'll stop here and then we'll pick up from here the next time, but also do more algorithms.